All right, we can get started. I do. I was about to say that. Actually, give me a second. At the end, everybody can pick them up. Yeah, so the first thing is I have some midterms here for those people that couldn't pick them up during class. So after discussion today, you can come up here and get your midterm. After discussion. Yeah. No, it's all good. It's all. All right. So today we're gonna start. I'm gonna start with a little bit of a review of what we did last week and kind of how you approach these bending problems. And I'll start first with a review of simple bending and the equations that are involved with it. There's a lot to cover today. I'm basically going to try to cover all of chapter 5 with exception of the multi-cell torsion and shear flow stuff because that literally would take too long. So I'll probably do that the next time, but I'll try to cover everything except for that. Hopefully I get through everything. So let's get started. With bending, right? You guys have done problems like this before. This is just kind of like a quick review of something you have seen in your other introduction classes. Right, you'll have a structure given, right, some beam, right, and they'll give you some loading condition, right. Let's say it's fixed at this end, and there's a point load here, P, right. In your previous classes, what you've done is done these shear moment diagrams. This is probably the simplest possible problem you could ever encounter, but I'll just do it for the sake of explanation. So that point load is going to generate both internal shear forces and internal moments throughout the structure. Okay? The reason I'm going over this is because a lot of people have been confused as to what these V's and M's are in the problems that we've been talking about. I'm just giving you a brief overview of what that is again. So this is going to be the shear force, and this is going to be the moment. This is just a quick review of these shear moment diagrams. If you have a force applied here, it has to be in equilibrium, right? So it has to be supported by the same amount of force in the y. So the sum of the forces in the y direction have to be equal. So there's a reaction force here pointing out, right? R, right? And the magnitude has to be the same as the applied force. So it's going to be P, right? So it's going to be equivalent to P. This force, this point load, also generates internal bending moments, okay? It's like you can imagine if you have this structure and you push it down, you're basically bending it, right? So there's internal bending moments acting through the structure. And so what we do with the shear moment diagrams is kind of describe the distribution of both the shear forces throughout the structure and the bending, these reaction moments throughout the structure. If we have this specific case, the way you typically draw these shear moment diagrams is you start at the base of your beam and you'll basically add the force that's acting. We're talking first about the shear force, right? So the magnitude of the shear force in this location at x equals 0, so this is x, right? At x equals 0, the magnitude is going to be P, right? So some arbitrary point P, okay? And that remains constant up until there's another force that acts on it. So at this location, it goes down by P. So this is also P, okay? So it starts at P is the same P, and then at this point it goes down by P, and at the rest of the beam here experiences 0 shear force, internal shear force, okay? Now, the moment is related to the shear force, namely this shear force is the derivative of M, right? So let's think about the moment that this P could be applying. If this distance here, let's say this distance is L, right? This beam is 2L, let's say. Then the bending moment that's acting at this specific location, x equals 0, is the force times the moment arm. So it's PL, okay? So, and it will be acting in this direction, right? Because it has to be in equilibrium, right? So if this is bending this way, this has to be bending, the reaction has to be in the opposite direction. And so that direction would be negative. So we go to the negative direction here. So this is the 0 axis, right? So this is the 0 axis for the shear and the 0 axis for the moment. So you go down to P times L. That's the magnitude of this moment, right? And like I said, this value, this constant value that you see here, is telling you that the slope of this is constant, okay? So the slope is going to be P. And if this is PL, then it's going to go down to 0 at a distance L, okay? And then at this point is 0, okay? So this is like a very simple example of these shear moment diagrams. And the reason I show this is because for these type of problems that we're talking about right now, you would normally have to do this process of finding V and M given the loading situation, and then you would use M and V at any given location. For example, in this problem, we would care about the base of the structure because this is where both the shear and the moment is at its highest magnitude, okay? So, okay, that being the case, right, we would have to do this first, find the location where these are the maximum, and then use these values V and these values M, and look at the cross section, because that's what we're doing in this chapter, right? Just looking at cross sections and looking at the shear flows generated and the normal stresses generated, right? We would get shear flows from this shear force, and we'd get normal stresses, sigma xx from these bending moments. So, just a brief introduction into that. What else? All right. So some basic equations that we covered last time, but I'm just going to write them down again. Basic equations for beam bending. So sigma xx equals my times z over iy. Okay? And that would be in the situation where you have, this is the x direction, this is the z direction, and the y-axis is into the plane, okay? And these are the bending stresses, normal stresses, generated from a moment, m, right? So if you were looking at this specific example, right, you find your shear moment diagram, you find that at the base, the moment is PL, right? You would go to this equation, plug in PL for my, and then find the location at which this is greatest, which is the highest z, which is either the top or bottom surface, and then divided by iy, which would be provided by the geometry of the cross section. Okay, this is in the case of unidirectional bending, right, with a symmetric section. There's a more complicated version of this where you have an unsymmetric section, and you could be given bidirectional bending. And so that equation, as we've seen before, sigma xx is a long equation, so bear with me. And then it's the same equation, I'm just writing it down here. Okay, so this is the full equation for any given problem that you got, right? If you have bidirectional bending, and of course you would plug in the position zy for whatever point you're interested in on the cross section, and find what the normal stress is there. Another important equation for these two, the relationship between the shear and the moment. It's not too important for this chapter, but just to have it in case you're given a problem where you first have to solve the shear moment diagrams, is, like I said, dm dx equals vz, in this case dmy, and dvz dx equals negative pz. Okay. And so yeah, this is the brief overview of what we talked about last time. Last time we talked about bidirectional bending and the normal stresses that are developed. We started talking about the shear stresses that are developed given a specific shear force, right? But we had talked about the fact that we're using this Euler-Bernoulli beam theory, and the issue with the Euler-Bernoulli beam theory is that it assumes that the shear stress or the shear strain gamma, what is it, xz, xy, I guess, equals 0, depends on how you define your coordinate. And if that's the case, then that results in a tau xy equals to 0. And that's the contradiction of the Euler-Bernoulli beam theory, because this is not 0, because we know for sure that there is some shear force at a given cross section. So if that's not 0, and we know there's a value here, then we have to find a way of deriving this tau xy from this v. And because we can't do it from the strain, so we have to find a different way of doing it. And we do that through equilibrium. So today we're going to be covering how to get the distribution of that tau across a cross section, right? Assuming, just an example of a situation, right? You have a beam and you have some solid cross section. We're going to cover different types of cross sections today, but just to begin with, we're going to cover the cross sections where the area is important, right? Like it's not like concentrated areas or thin walled sections. These are like solid sections. If you have some applied P, you're going to have a distribution of this shear force across, where it's going to be constant in this case. But that constant shear force V, right, Vz, is going to produce some tau xz, right, some distribution of that across the cross section, right? We're interested in finding out how that tau xz varies from top to bottom. Okay, and there's an equation for that, and I'll derive it here, I guess. Let me see. Yeah, so we're interested in tau xz and how that varies with z. Okay, whether it's parabolic, linear, all this stuff. So we're going to start first with chapter 4.3.1. So 4.3.1, and that's a narrow rectangular cross section. All right. So we're given the following cross section. It's a solid cross section, right? These are not webs. And the dimensions are h over 2, h over 2, b, right, centroid. Okay. We know for sure that there's a relationship between the shear force and the shear stress throughout the cross section. And that relationship is simply Vz equals, in this case, b times the integral of from negative h over 2 to h over 2 of tau xz dz. Okay. However, so we know that relationship is true. However, even if we were given this number here, we wouldn't be able to derive the distribution of tau xz. So we have to find a different way. That's what I was mentioning earlier. And the way we do it, like I said, is from equilibrium. So this is probably the only derivation I'm going to do today because there's a lot of examples I want to cover. So we start from equilibrium, right? And so from plane stress, the equilibrium equation is the following. Okay, do you guys know the equilibrium equation? We also know that sigma xx, all we're trying to do here is find an equation for tau xz. Just follow with me here. So sigma xx we know that is related to the bending moment my times z iy. Okay, talked about that over there. We also know that my is related to vz. So if we rewrite this actually before we go to that step, as dm dx so it's the same equation, just rewritten in terms of the moment. But like I said, we also know the relationship between the moment and the shear force, which is dm dx equals to v. Right, it's my in all these cases. And so if we use that relationship, we can rewrite the equation in the following way. d tau xz dz equals negative z vz iy. Okay? So now we have this equation, this differential equation, that relates vz to tau xz. And from here, if we integrate this equation, then we can find an equation of tau xz as it relates to the z position. And so that's what we'll do now. All right, so we have that differential equation. And so what we're going to do is we're interested in finding, we'll choose an arbitrary z position, right? Let's say this location here. This is z. All right, we want to know what tau is at that point. Okay, the reason they talk about narrow in this title here, narrow rectangular, is because we're also assuming that this tau xz doesn't vary with the y coordinate system. Okay, it's constant. So it only varies with z. It might be large here, small here, whatever, but it's going to remain constant through the y dimension. Okay, that's the importance of this narrow word right there. So if we integrate that equation from negative h over 2 to this position z, we get the following equation. We get the following equation, right? This the left side, right side. We also know that in these problems, typically, or for all these problems that we're doing, the shear stress has to be 0 at the top and the bottom because it's traction free. So in order for that not to be 0, just because there's been some confusion about this as well. All right, if this is the beam, looking at it from the side, regardless if the force is applied like this, there is no shear stress in that direction. In order for that to not be 0, there would have to be a force parallel to the top surface. But we haven't experienced a problem where that's the case, and such a loading is kind of weird. I don't think we see it in any one of these examples. So the top and bottom surface are considered free, right? So tau xz at this location is 0. So if that's 0, then the equation can be written also as tau xz equals okay, so that's the equation where C equals h over 2. The important thing to note about this right here is the fact that it's a parabolic or quadratic distribution for the stress. Okay, so we go back to our cross section. We know that tau xz equals 0 here, and it equals 0 here, and we know it's a quadratic distribution. The distribution is going to be like this. Okay, and there's going to be the maximum is going to occur right at the center. So this is tau max. And the value for that is we basically have to plug in y or z equals 0, which would result in just tau max equals vz c squared over 2 iy. So that's the maximum, and it occurs at the center. So a lot of times people get confused with these diagrams, right? Where I draw the magnitude of the shear stress kind of to the side. This is not telling you anything about the direction it's occurring in, just the magnitude, right? If I drew it as a line, it would just still say what the magnitude is. The actual distribution of these, like I said, if we draw it as arrows, right? In this problem, I don't know where the direction of VZ, but let's assume it's pointing down. The distribution of the shear flows, right? It would be 0 at the top boundary, right? It would be constant, and it would increase, and the biggest arrow, right, would be right here in the middle, and then it would go smaller and smaller and smaller, right? So on and so forth. I can't draw these arrows. So that would be the actual, that's how the distribution of these arrows would look. This right here is just to kind of demonstrate that as far as magnitude goes. I've had some people ask me questions about that. Okay, so that's it for the narrow rectangular cross section. It's the simplest case because the distribution in the y direction is assumed constant, so we don't have to worry about that. So we can always solve for tau, right? However, there are sections where this dimension can't be considered narrow, and therefore there's going to be some distribution in the y direction. And that's often too complicated to solve for. So what we solve for in those problems, rather than tau, we solve for q. Remember the shear flow? Right, so we solve for q in any cross section where the dimension y might not be constant, or it's large enough for there to be some variance. So I'm going to do an example. So this is chapter 4.3.2. All right. So 4.2.3. General symmetric sections. So the way this chapter is structured is, all these chapters in this book are structured in the following way. They go through the simplest possible case, and they start adding more complexity, and eventually they land at the most general possible equations. I could start by giving you guys the most complex equations, but I think it might confuse some people, so I'm following the flow of the book in this case. So we're starting with this narrow rectangular. Now we're going to general symmetric sections. So there's still this caveat that these sections are symmetric. So there's some simplifications made. As we progress, there will be unsymmetric sections and thin-walled sections and all kinds of stuff that add complexity to these equations. But for the sake of explaining this well, I'm following the same flow as the book. So if we have a cross section, for example, like a trapezoid, okay? So this is no longer a narrow section. So if we look at some location Z, right, let's say this location Z, the shear stress might vary with the y coordinate, okay? So the magnitude, right, might follow some distribution that we don't know. Okay, so tau xz might be some function of y. Since this is not uniform, right, it's hard to solve for the distribution in that direction. So typically what we're interested in, like I said earlier, is finding the shear flow, right? If you guys remember, the shear flow, basically it's called QZ, divided by the thickness is going to equal tau xz. If the stress is not uniform, then we add that bar. That signifies that that's the average shear stress. As opposed to without the bar, it would mean that it's constant. Like in this case, tau is constant throughout the y direction, so it's just tau. Here we don't know the distribution in that direction, so we assume an average, okay? In these problems, we're trying to find Q, and the equation is going to be slightly different. And so whenever we solve for Q, if we divide that Q at any given Z position by the thickness at that location, we'll get the average tau xz. We might not get the exact tau xz at any specific location, but we'll get the average. And that's still valuable. Just keep that in mind, that if the distribution is not uniform, then we're solving for this average. Now the question is, how do we solve for QZ? So that's the variable of interest now. All right. So the way you approach this, I'm going to draw the cross section again, a little bigger. Okay. The way you solve these problems is that you find the centroid. We've gotten pretty good at doing that at this point. Define your axes, right? This is the y, z plane. And let's say that we're trying to find the shear stress at this position z. Right, so this is z. So we'll call this distance here z1. Okay? The goal here is to find tau xz at z1. How do we do it? I'm not going to derive the equations. Like I said, there's a lot to cover today, so I'm just going to give you the equations. So the equation to solve, first, I said tau xz, but first we're going to solve for QZ. So the shear flow, it's the same thing, right? You have to just divide by the thickness at that location. QZ, as a function of z, is going to be Vz times big Q over Iy. Q, in general, it's defined as double integral a1 z dA. But as you may have noticed now in this class, anytime there's integrals, you don't really have to do any integrals. So typically, for these problems, you just multiply an area by the position of the centroid. So let's call it A1. Let's see. That'll make sense in a bit. So we're trying to find QZ at a certain location Z. We would be given the shear force, and we could figure out the moment of inertia about the y direction, just based on the geometry. We've done plenty of examples doing that. Now the main thing for these problems is finding this Q. Okay, so what is that Q? That's known as the first moment of area. So you would basically make a cut at whatever location you're interested in finding Q at, right? So let's say we're looking for a Q, the shear flow at Z1. We'd make a cut at this position, and then the area above it above this cut, right? That would be, let's call it area 1. Okay? And to find Q, we would multiply that area 1, right, meter squared, times the z position of the centroid of that area. Okay, so we have this other shape here. It has its own centroid. Okay, so that will have a different z value, zc, and that's what I've drawn there. So you would take this shape, find the centroid, easy enough, cut it at whatever location that is relevant to whatever you're looking at, and then at that location you'll have an A, you have a Z position. You'll have to find the centroid of the new area as well, and then you're given all the other values, and you can solve for Q. Okay, and now that you've solved for that, then you can easily solve for tau xz. Right, so tau xz, the average in this case, is qz over t. All right, and so what is t in this case? It's this dimension. Okay, so this dimension is t. Yeah, so simple enough. You can find tau xz. All right, we can move on, I think. Questions about this? No? All right. So in your test, in your final exam, you probably want to encounter a problem like this with these solid sections. These solid sections are not too relevant to the aircraft structures that you'll be analyzing. Typically, we'll be doing these spar web structures, so that's what I'll be covering next, or thin-walled structures. However, this equation, VZQIY, this is basically how it's done even for the thin-walled sections and for the spar web sections. The only difference is, keep in mind that these equations that I've derived here are still for symmetric sections. It's not the most complex version of them, and I'll get into those, but just for the sake of explanation, again, that's how it's done. So now we'll go into chapter 5, which is the one I'm gonna try to cover today. I'll see if I can get through it. So 5.1, this is flexural shear flow. In open thin-walled sections. Okay. All right. So instead of going through the derivations, we're just going to do an example, and I'm going to try to explain it as I do the example. This example is actually one from your homework, but I think it's very good for explaining what this topic is, and I wish I had done it last week so you guys could have known this prior to the homework, but it is what it is. So we're given a specific cross-section, right? You guys have seen this cross-section before, thin-walled, just like a box beam type situation. However, in this case, it's cut at this location. It's a very small cut. Okay? The dimensions they give us is that this from here to here is 100. And this one is 200. And the thickness is 2 millimeters. These thicknesses values are actually pretty important for these problems. It just adds a bunch of little numbers to your equations. And the way and also VZ, they're giving you VZ in this case, is 1,000 newtons. And it's acting at the shear center. I'll cover what shear center is, but just keep in mind that it's a VZ that's acting on this, right? Again, just to reiterate, if you're not given VZ, but you're given a beam problem with some loading condition, you could find VZ doing the shear moment diagrams. You find that, then you apply it to the cross section. Okay. Step 1, you guys have this memorized by now, is find the centroid. The centroid's easy to find here, right in the center. It's a small cut, doesn't change anything. Centroid's there. So we're not going to focus too much on finding the centroids and finding the moments of inertia. That's played out. We already did that last week before that. So step 2 is moments of inertia. Find the I's. In this case, interested in IY. Yeah. Okay. So IY, in this case, the equation, I'm just going to write it out. Okay, that's the equation for that. Ends up equaling 6.66 times 10 to the negative 6, I think. Yeah, 0.002 because you have to add it to the top and bottom. Yeah, the half and half. Okay, so you can find that. The explanation for why the equation looks like this is they're basically taking the moment of inertia of the big rectangle and then subtracting the moment of inertia of this inner rectangle. So that's all that's happening there. Remember, moments of inertia, you can add them, subtract them. It's easy, right? Simple as that. You guys can do examples on that if you need more information. The third step is where things start getting interesting. Is step 3 is set up the coordinates, your S coordinates. Okay, so for problems now on, in these thin-walled sections and the spar web sections, we're no longer dealing with tau xz or tau xy because the coordinate system may not align exactly with the direction of the shears. So we're going to be dealing now with tau S and tau n, mostly tau s. Okay, what is s? What's the s and n? So the s coordinates, we're using s n coordinates now. Just for this. We're still going to use xy coordinates for all the other equations, but just to make sure the taus that you get may not be tau xz or tau xy or tau x whatever. The reason for this is that the s coordinate is the coordinate along the perimeter of whatever location you're looking at, right? So for example, S here points in this direction. S here points in this direction. S here points in this direction, so on and so forth. And N points perpendicular to that. So here, it always points like this, right? So you guys got that, I hope. All right, so now we have to set up our S coordinates, okay? And so the way you do that for these problems, for these open, thin-walled sections, so remember it's open. You'll start at one of these open ends and you'll set up your first S coordinate, okay? So in this specific case, we'll go here and set up S1. So S1 starts right there and it points up, okay? Whenever S changes directions, we're going to set up a different coordinate system, S2. Well, it doesn't have to just change directions, right? So it's basically, you can't define this length here in terms of S1. So we're going to set up an S2 to kind of split up the problem into multiple steps, right? So at any given different length, we're going to set up a different coordinate. So this is going to be S2. And then from here down, it's going to be S3. All right? And we're just going to focus on those first, S1, S2, and S3. you could call this S4 and S5, but there's an easier way of doing this. So we're just going to focus on those three first, and then we're going to explain where S4 and S5 and S6 come in. So, okay, hopefully that makes sense. Then the next step is solving for these big Q's. Right? That's still the variable of interest here, because from these big Q's, these first moments of area, we can figure out these shear flows, and from the shear flows, shear stress. From the shear stress, we know if the structure is failing or not. So that's what we got to do. Find Q, big Q. All right. So we start the problem at the first coordinate that we set up, so at S1. So now the goal is to solve for Q at S1. So remember, S1 varies, so Q is also going to vary as S1 varies. We're trying to find a function for Q that varies with S1. And so the equation for Q, you guys remember, just wrote it down, is AS times ZC. Okay, so what does that mean? Like I said, in this case, basically what we're doing is taking this coordinate system, looking at a position, some position S1, right? S1 varies from 0 to 100 millimeters. Okay, we're trying to see how this Q varies from there. So the equation that we would get is that the area, right? So let's say we're looking at this location here. All right, the area is going to be here. All right, so that area is going to be AS. Okay, so how do you find that area? Well, in this case, it's just the thickness times the position S1. So S1 times T. And now we're interested in finding the Z position of the centroid of that area, right? So it's just a rectangle, so the centroid's at the half of the height. So this is the centroid here. Not the centroid of the original structure, the centroid of this location, right? So what is it there? It varies with S, right? As S increases, it's always going to be S over 2, S1 over 2. So I'll just write that down. .001 S1 squared. Okay. Now we know Q. The goal now is to find shear flow. There's a relationship between those. So QS equals negative BZ times Q over IY. And so we plug in the numbers here, 1,000 times 0.001 S squared, 6.66 times 10 to the negative 6 equals negative 1.5 times 10 to the 5 S1 squared. All right, so this is how the shear flow and also the shear stress vary with S1. As you can see, it's a parabolic distribution. What you'll notice is that for these problems is that if you have a shear force acting in the same direction as the length of whatever structure you're looking at, if VZ is acting vertical, I mean it has to act vertical, and you're looking at a vertical portion of one of these structures, the distribution is going to be parabolic. If it's perpendicular, for example here, it's going to be linear. Parabolic, linear, parabolic. Okay, that's a quick thing to just check your answers. Like if you get something linear here, then you're doing something wrong. So we have QS. And now the next step, so now we know how it's distributed along that portion there. The next step is to go to the end of that S1. So we're going to take it to the maximum possible location. So here, we're trying to find QS at the maximum possible location. So QS at the end of S1, and so at S1 equals 0.1 meters, I think that makes sense. Yeah, 100 millimeters, yep. Then QS is going to equal negative 1.5 times 10 to the 5 times 0.1 squared, and that's going to equal 1,500 newtons per meter. Okay, negative 1,500. All right, so that right there is the maximum shear flow for that portion, negative 1,500 newtons per meter. The negative, here it's important, if you get a negative using these equations, then it means that the shear flow that's actually occurring in the cross section is in the opposite direction to the coordinate system that you chose here. So if S1 is pointing up and we got a negative, it means that the real shear flow is pointing down. So we'll draw that at the end, so just keep that in mind. And so this is basically the entire process, but now we're going to keep going for S2 and S3 and so on and so forth. So I'm going to erase this. Hopefully everybody got it. So we're going to solve now for Q at F2. All right, so the key here is that this big Q, right, this big Q, this first moment of area, you're going to be progressively adding it as you move along the whole contour, right? So from here to here, we found what Q could be, big Q, right? The first moment of area. That value is going to be the starting point for S2, and then you're going to add more first moment of area as you progressively increase here. So we're going to start at the maximum possible first moment of inertia that came from S1. Okay? So the equation for Q is going to be a little longer now. Q equals 0.001 times 0.1 squared plus 0.002, oh shit, what the hell, 2 S2 times 0.1. Okay, and if we simplify that, it's 10 to the negative 5 plus 2 times negative 4 S2. All right, so let's look at this equation. This is the Q from S1, right? The maximum possible location, right? We go here. The area, what's the area? Thickness times the maximum S1, which is 100. So thickness is 0.001. What? Oh no, half the thickness. Yes, half the thickness. So we're only going to this half point. That's an important fact here. That makes sense? Wait, why is that 0.001? Anybody help me out here? The IY? What? All right, if you say so. I believe you. All right, so basically it doesn't matter if it's 0.1 or point whatever. this has to be the maximum possible value of big Q for that first coordinate system. And then this is how Q changes with S2. Okay, so how does Q change with S2? You make an arbitrary cut at some location, right? This area is going to be the thickness times S2, right? So 0.002. Maybe that's supposed to be a 2 nose, I don't know. So 0.002 times S2, right, times the Z position of the centroid. But as you can see, this is not moving up and down, right? It's always at the same height. So it's a constant 0.1, okay? So that's 0.1 meters for that Z position. What that ends up giving you is that, for the vertical position, you would have another S value here. So you would have some squared term here. But here, we only have a linear term, okay? So this is how big Q varies with S2. QS, the shear flow, right? We can get that from the first moment of area. It's going to be negative VZ times Q over IY. We plug in the values for that, right? We're given this. We found that earlier. So negative 1,000 times 10 to the negative 5 plus 2 times 10 to the negative 4 S2. 6.66 times 10 to the negative 6. That equals negative 1,500 minus 3 times 10 to the 4th S2. All right. So that's how the shear flow varies with S2. And as you can see, it's a linear distribution as opposed to that vertical portion where it was parabolic, quadratic. All right, and then we do it again, do this whole same process again. Actually, before we do that, we find the maximum QS, okay? So the maximum QS, so QS at S2 equals 0.1, right? Because that's the width of that structure, so 0.1, that's going to be the maximum, is going to equal to, we plug in the values, negative 4,500 units per meter. Again, that's going to be pointing in the opposite direction as S2 because it's negative. So simple enough. Now we go to Q3, or S3 I mean. All right. That 0.1 has tripped me up for real. Let me see. Who knows? I'll look at it later. So now we go to solve for Q for that third coordinate system. And then I'm just going to write it and explain the terms. Q is going to equal 0.001. There it is again. 0.002, 0.1 squared plus 0.002. Who knows? That's crazy. Okay, so we're adding the maximum, this from S1, this from S2, and this is how it varies with S3. All right, so this is a constant addition process, right? You go to the maximum here, maximum there, and then we make a cut here, for example. You have this area, so the area is going to be that S3 times the thickness. So that's simple enough, and then times the position of the centroid, which in this case would be half of this, half of whatever S3 is, but we're defining it from the original coordinate system, right? So This is YZ. So that Z position, right? If this is 100, right? That's Z equals 100. Then it's going to be that position there is going to be 100 minus S3 over 2. That's the centroid of whatever location you make that cut. Okay? Does that make sense? Yeah? All right. So simple enough. And then except for this, not simple enough. Still tripping me up. But we're going to ignore it. And then the shear flow, same old thing. Negative VZ, Q over IY. Plug in the numbers. I'm not going to do all that. End up 1500 minus 3 times 10 to the 4th. S. Nope, that's the wrong one. Sorry about that. That didn't make no sense. Okay, it's negative 4,500 minus 3,000 S3 plus 150,000. It's completely different. S3 squared. So, yep. So that's the distribution of the shear flow on this vertical portion here. And okay, let me see. Yeah. So like you can see, it's also parabolic, so which makes sense to what I said earlier, right? If you have a force, let's say if you had Vy in this case, then these would be parabolic and these would be linear. If you had both, then both would be parabolic. Here we only have Vz, so only the vertical portions of this have this distribution. So we have that. And from these equations, again, you can plug in whatever value you want for S and find the shear flow, then divide by the thickness, which in this case the thickness is always constant, 0.002. Then you can find the shear stress. Okay, so just keep that in mind. We're not going to do it for this problem, but you could do that if you were asked to do that. And now there's still this other bottom half of the structure. You could, take S3 down here, S4, and keep adding these terms and make these long equations. It's not necessary. What you could do for these problems, for this one is, it's not super helpful to do what I'm about to describe, but there are cross sections where it's more helpful. You can always start a new coordinate system at any open location. So we could define this to be S4. Okay? If we define that as S4 and just make sure you keep your positives and negatives correct, you could just find the equation. It would be the simpler version of instead of adding everything. You just go this direction and it will give you the same answer. So you could start S4 here, solve for Q, solve for shear flow, then add this one. And you'll end up finding out that for this problem, since it's symmetric about the y axis, the distribution is basically mirrored. Okay, so now let's draw what that distribution is. Oh, I forgot. If we find the max of this, so Q S max for that third portion equals 6,000 newtons per meter, negative. So you guys know what that means. And now we're drawing the distribution of this. Damn, time's going by fast. All right. So we have this cross section. It's not perfect, but whatever. We know that I forgot to stress this, but hopefully it made sense. At the cut section, right, the location of the cut, this shear flow is always going to be 0. Okay, so you always start with 0, and it increases. Well, why does it start with 0? It starts with 0 because there's basically no area, right? This Q increases with area and the Z position of the centroid, right? So it starts increasing, and you can imagine at the beginning it's always 0. So we're going to draw the magnitude and how the magnitude of the shear flow changes, right? So it changes parabolically in this portion here. Remember, then it goes from here, linear, so this is 0, 0. This is the max, 1500. This is 1500 as well. 45 up there. 45 here. 6,000. It's the one I just wrote down over there. 45. 1500. 1500. Okay, so the distribution of the magnitude of the shear flow would look something like that. Remember, these diagrams here have nothing to do with the direction of the force applied or anything like that. It's just showing the magnitude and how it changes along the length of the structure. And now what direction it's acting in, we got all these negative numbers, right? So we had defined the shear flow to be positive in that direction, or not the S dimension to be positive in that direction, but we got all negative numbers, so we know that the shear flow has to be pointing like this. Jesus Christ. Okay, so that'll be the direction of course, these arrows are not drawn to scale. Go ahead. Yeah, the numbers at the endpoints are important because those are typically the locations where it's like maximum, right? So, for example, for this structure here, we would want to know that this is the maximum location of shear stress, right? Of course, you could have the distribution, but we would know what the value is. We want to know what the value is as well, right? So, yeah. I mean, you don't. The one thing is you don't have to draw the shape exactly parabolically or the slope. It doesn't matter. Just the general linear, or just draw the shape, whether it's linear or quadratic, and add the values. Yeah. Are you asking because you didn't do that on the homework, or what you saying? Yeah. Oh, don't even trip about that. Don't worry about it. Doesn't matter. I don't think they'll grade for that. Well, I don't know actually, but we'll find out. Okay, so that's for that cross section. This thing I mentioned about starting at any open location, right? It's not super beneficial for here, right? Because we could have just taken it progressively from here to there to there to there, and just keep adding these terms. However, for other types of cross sections, for example, this I-beam looking thing, there's a bunch of open starting points. Okay, so let's say we have some VZ acting on it. Okay, we have VZ. Another thing to clear up right now. So far, we haven't talked about the location at which VZ is being applied. That matters because if VZ is acting here or here or here, it's going to produce different results as far as torsion goes. It's not going to produce different results as far as this distribution goes, but you can imagine if this VZ is applied at a very far location, it's going to also twist the cross section. We'll talk about that in a little bit. So far in these problems, all you're being told that there is a VZ, not where it's acting. Eventually we'll have to find where it's acting or where it should act so that it doesn't produce torsion. But going back to the topic I was just describing, for this specific cross section, you can't just add it progressively, right? It's not a little loop. Right, so you have many open-ended sections, right? So we could define this as S1, okay? But then, I guess you could make this S2. But then you're ignoring all the first moment of inertia of this portion, right? So you also have to have a starting section here, right? So let's call this S2 and this S3. So the way you would do it, right, is solve for the shear flow from here to here, shear flow from here to here, using this other coordinate system. Then add those two, the big Q's, and then go for 3, okay? And then you can do the same thing down here, right? So S4, S5, S6, whatever, right? And you would find that if we're looking at distribution, if we just have a VZ, we would have a distribution like this, something like that, okay? And then if VZ, let's say it's positive, so if it's a positive number, let's say 1,000 or something, then the shear flow would look something like this. And the direction of the arrows always kind of makes sense. Like when you're thinking about shear flow, it's as if it was like water flowing, right? This one, for example, wouldn't go to the right. It's like if you have a stream going this way, it would split up, and these both would come together there. So intuitively, the drawing of the shear flow arrows should make sense. So that's a case where you would have multiple starting points for your S coordinate. All right, now we get a little complicated. So far I think it's been relatively simple. Now, like I've been saying, I've been describing possibly the simplest case where you have only VZ and you have symmetric sections. So the equations are relatively simple, right? That VZ times Q over IY. That again is the simplest version. So now I'm going to write the more complicated version, or the more general version, I should say. All right. Okay. So that big equation, I shouldn't have erased it, but I did. The big equation of the normal stress when it comes to bending, I'm going to rewrite it again, but just including some constants that are going to be relevant for the rest of the equations. Right, so sigma xx equals ky mz minus kyz my, y position, plus kz my minus kyz mz z position. So that's the same equation that you guys had seen previously, except we've replaced a lot of these moments of inertia terms with these k's. So what do these k's mean? Ky equals Iy over Iyz. Nope. Sorry about that. Iyz minus Iyz squared. Kz equals Iz over Iy Iz minus Iyz squared. Kyz equals Iy, Iyz over Iy Iz minus Iyz squared. Okay? So, all right. Then with these K terms, we can rewrite the shear flow equation, right? The one that we had previously just seen where it's Vz times Q over Iy. Like I said, that's a simple version. The complicated version, I'm going to write it out, and it has these K terms. So Qs in general is negative Ky Vy minus Kyz Vz Qz Kz Vz minus Kyz Vy Qy. All right. So this is how you approach the most general version of the problem. And this is assuming that it's an unsymmetric section, and also that you have this bidirectional shear forces, Vy and Vz. Okay? It looks complicated. There's a lot of terms, but in general, it's the same thing. You just got to remember the equation. For a lot of the problems that we'll do here, we'll typically only consider one of these forces, Vy or Vz, because it makes it a lot simpler. There's a lot of terms we can eliminate when we do that. And again, if it's symmetric, then we could make another big simplification, meaning that Iyz is 0. Right? You guys remember that? So that simplifies everything. So keep this in mind. We're not going to do an example where we have to do all this, but just this is important in case you're given the most general problem you could get. So, all right, now we're going to do spar web sections, and I'm going to try to do it fast because we're kind of running out of time here. Are we? Yeah. Okay. So these problems that we've done here with these shear flows, the area changes as you move across the length of the contour. It increases, right? So that's why you get these parabolic distributions and all this stuff. And those are actually harder to do than the spar web sections. Spar web sections are a little bit easier. So I'll do an example. I don't even know if this is an example. I just wrote it down. I don't know what I'm just going to copy down what I wrote. I have no clue what I wrote, but let's see what happens. All right, we have this section here. Okay, so it is unsymmetric. So this is A. Okay. This is H. This is 2H, and this is also H. And they tell you that VZ does not equal to 0 and Vy equals to 0. So that simplifies the problem a lot. And so the question is, how do you approach these problems? Same exact approach as we described previously. You start at an open end, define your S1. In this case, we'll start up here. So S1, we'll call this S2, and we'll call this S3. Simple enough. But let's follow the steps that we outlined. So the first thing, right, is centroid. So that's easy. In this case, it's right here. Right. So this thing is not perfectly symmetric. I mean, it is symmetric about the, actually it's not symmetric, I'm tripping. No, not symmetric at all. So centroid, and then moments of inertia, right, so the I's. So in this case, it's Iy equals 4h squared, Iz equals 2a h squared, and Iyz equals negative 2a h squared. Wait, is that a 4 or should that be an A? I think there should be an A here. Yeah. Okay. So 4a squared, yeah. All right. And then for these problems, since it's unsymmetric, right, you find the k's from that equation. So you already have those values, so we could just find the k's. So ky equals what the fuck, man? I guess this is just ah squared. I'm tripping. I gotta check these numbers, but just follow the general procedure. Kz equals 1 over 2a h squared, and kyz equals 1 over 2a h squared negative. And then we follow the same procedure as before. So we're going to calculate, so step 4, calculate big Q and little q for each one of these coordinate axes. So we start at S1. So at S1, Qy equals A times H, Qz equals negative A times H. Okay, so the important thing here is to remember that these webs don't add any area, right? So in the previous examples, these had some thickness, some non-negligible thickness, so the area would keep increasing as you move down S1. In these problems, this web has a negligible area, so the only area that matters is the area with which you start. So in this case it's A, and it's going to be A throughout this whole length. All right? And so Q is going to be A times the position of the centroid, the Z position of the centroid. In this case, it's going to be A times H, because you know that height is H. And then for QZ, it's going to be let me see. Yeah. So this is the centroid, right? So this is where we define our original axis. YZ. So then the centroid in the Y direction is going to be negative H. So that's why this one is negative. All right. So in this case, we have two Qs. All right. And so now we plug those in to the little q equation. So Q1 is going to be KYZ, VZ, QZ, minus KZ, VZ, QY. If you plug all that in, you get 0. Wonderful. Now we go to S2. Same thing. So S2, we have QY equals 2AH, and QZ equals negative AH. Okay, so why these values? You're basically adding both of the areas for S2. All right, so you're making a cut here, let's say at any arbitrary position S2, and you're going to add the relevant areas that are above that line, before that line. So there's two A's here, and the centroid is at H. And then for QZ, the Y position of the centroid for this one is 0, so you can neglect that one, so you still only left with this one being the relevant one. So you got that. Because you can see it's a lot easier now, right? You don't have to do these linear equations and stuff, so it's a lot easier. And so Q2, we plug in everything. It's going to be negative 1 over 2AH squared, negative AH VZ minus, this is a crazy equation, 2AH squared, 2AH VZ. That all equals negative 1 over 2H VZ. And there's nothing for Q3, but you could do the same thing. All the areas before the relevant things, find the Q's, QY, QZ. You find Q3. And again, to find the shear stress, take those Q's. In these cases, they're constant values. So you'll have one value here, one value here, one value here. You can divide those by the thickness and find the shear stress. So simple, easy peasy. And now what I think is the most important part of this discussion, and the last part, which is good, is the closed thin-walled sections. It's been pretty confusing for some people, so hopefully I can explain it well. All right, so this is section 5.3, closed thin-walled sections. And this is single cell. Okay. Like I said, I'll cover multiple cell next time. There's a layer of added complexity. It's not too difficult, but if you can get this, then you can get that. All right, the idea behind this, it's a little weird. So let's assume we have a thin walled section. Again, this is not a solid section, right? These are just, let's say, webs, okay? We're trying to find QS as it varies with S, right? So the distribution of the shear flow around this structure. The way we're going to do that, since we don't have an open section to start with, we have to do this approach a little different, right? So what we're going to do is take that same structure and split it up into two different structures. We're going to split it up into one that we can solve, that we know how to solve, like the open walled sections, right? So we'll make a cut here at some location. You can choose whatever location you want, all right? And that's going to, you can solve that. We just talked about how you solve that. Right? We start an open end and you continue, blah, blah, blah. Simple as that. So that'll give you QS prime as it varies with S. Right, we'll call that QS prime. However, that, of course, is not that. Right? So there's a difference between this and this. And basically what you're missing when you solve this is the shear flow that would have occurred here that you got rid of by making that cut. And that shear flow is constant throughout the entire section, and we're going to call it a constant Q naught. Okay? So that's constant throughout the whole thing. So here. Right. So again, we have a closed section. We're going to make a cut, solve for QS prime, which we know how to do. We just did a couple of examples. That's easy. And then we have to somehow solve for Q naught, which is a little confusing. But once we solve for Q naught, we add this, and this is the real result. Okay? So I'm going to break it down into steps. I need some water. All right. So step one, as you can guess, centroid. Step two, eyes. Step three, find the Q primes, right? So make an arbitrary cut, find the Q primes. You could do that. Step four, find Q naught. How do you find Q naught? Let me see if I can explain this right now, or should I wait for the example? All right, so the way you find Q naught is that, let's say you have this structure, right? Say it's like this, right? And you have an applied VZ. In this case, they tell you the location of the applied VZ. All right. That VZ is generating shear flows on all of these webs. Right. So you have all these little arrows, right, acting somehow. Okay. What you have to realize is that these shear flows will generate a torque about any given axis, right? If I choose, for example, this point to take the axis, right, about where the things are twisting. You can choose any given location, but let's say we choose this point. Then this shear flow won't produce a torque. This one won't produce a torque. This one won't either. This one will produce a torque. And that torque, right, so this force times this distance has to be equal to the torque generated by that. Okay? That might be a little confusing. Hopefully it makes sense in a bit. But the equation, let me see. Yeah. So the equation that you're going to have to use is VZ times D All right, so this is the equation you're going to have to use. Vz is going to be a given value. D is going to be the distance from the x-axis, so the centroid, so the perpendicular distance, right? This is the torque generated from Q0 or Q naught, right? If you guys remember from the torsion chapter, that's the equation for a constant shear flow around a closed section. 2 times the area enclosed times that shear flow. They'll give you a torque. And then also the moments produced by the Q's about the x-axis. Okay. All right. And then step 5, I guess. Yeah. This won't make much sense until I do the example, but it'll make sense. Step 5 is to find Q. Okay, the real Q. At this point, we found this, and we found Q naught. So all you got to do is just add them. So Q equals Q prime plus Q naught. Simple as that. And 6, it might be an optional thing for the problems, is to find the shear center. Okay, so what is the shear center? The shear center is a position about which this VZ, right? So this VZ could be acting anywhere, right? It could vary along any position Y. There's a specific position Y in which it will produce no torsional deformation, okay? In this case, like if it's perfectly symmetric, like in this case it's a perfectly symmetric system, if VZ was applied right down the middle, that would be the case. It wouldn't twist, okay? If it wasn't right through the middle, if it was to the right, to the left, this cross section would rotate a little bit. And so the shear center is that location Y about which VZ should be applied to reduce this twisting deformation. This might be intuitive here because it's symmetric, but if this was not symmetric, then VZ has to be placed somewhere else so that it doesn't twist. Okay, that's the whole idea behind shear center. So let's do an example and we'll get out of here. Last example. Where's the... All right. All right, example 5.6. All right, so in this case, we're given the following section. They tell you that the spars have an area AA, right? They're the same amount of area. These have 2A, these have 2A. So it's symmetric about the y-axis, but it's not symmetric about the z-axis. Okay. The dimensions here are h. And this thing is thickness t. So everything is left pretty general here, which is good. All right, so step 1, find the centroid. I'm not going to go through that. You guys know how to do that. Ends up being, right, if it's symmetric about the y-axis, you know it's going to lie about the y-axis, but then you can do the rest of the equation to find c. You'll end up finding that it's right there, which is 2h over 3 distance right there to the right. And that's where you define your coordinate system. Okay, remember that? Zy. Then you find the moments of inertia, right? So we end up finding Iy equals 3/2 ah squared. Iz equals 4/3 ah squared, and Iyz symmetric, so it's 0. So step 1, we start by assuming a cut at some location. All right. So we're going to call this, I'm just going to draw this again because I did that here. So we're going to call this spar 1, 2, 3, and 4. So these are the QS's. So this is going to be Q12, Q23, Q34, and Q41. All right, we're going to have to solve for 4 different shear flows. The good thing about these thin spar web sections is that whenever you make the cut, this whole thing goes to 0, right? Because these areas are negligible. So that's good. All right, so the first step here is to find these Q primes. I forgot to put the primes here. All right, so these are primes. Over here we have the real Qs. So Q12, Q23, Q34, Q41. So that's the final goal. First is this. Okay, so we're going to do the same thing we did previously. I got it. Oh, what's up? Y'all trying to get in?
Yeah, sorry.
All right. Where are we at? Okay. So Q12 is we're going to start with the open. Always start with the open location. So Q12, like we said, Q prime is going to be 0. Thank goodness. That's simple enough. Q23 prime, it's going to be VZ times A H over 2 over 3/2 AH squared. So that ends up equaling negative VZ over 3H. Same equation as before. Am I missing some? Negative. VZ times Q over IY. Q here makes sense, right? It's A times the position, Z position of the centroid of this, right? So we've made the cut here. This is the only one that matters. Z position is H over 2. Then IY, we calculated it. 3/2 over AH squared. So simple enough. And then we follow the same procedure as before, and we find the Q34 prime. You add the values, and you end up getting that this cancels out with whatever you get at the bottom, so this is actually 0 as well. Q41 prime is negative VZ times 2A times negative H over 2. 3/2 AH squared equals 2 VZ over 3H. Okay? So we have only these 2 shear flows that are non-zero. So we're halfway done. Now, remember we split it up into 2 problems. Now we're going to find this constant Q naught. So how do we do that? Give me 1 second, guys. I might have forgot. Oh, yeah, I forgot this. Yeah. So the VZ, they tell you where it's applied. Okay. So VZ is applied there. So that's good. Okay. And the value of it, I don't think they give us a value, but it's important to know where it's applied. So now to find Q naught, the last step is basically you got to set the moments generated from VZ about a certain axis equal to the moments generated by the shear flows about that same axis. Okay. In this case, we choose this spar to be the axis of interest. So is that right? Q23. Yep, that's the one. So we find Q naught by setting the moments from Q and V equal to each other. Okay, so if we're looking at that moment generated from V at that location about that spar, it's VZ times 0. It's good, simplifies the whole thing. And then we're looking at the moments generated from Q naught and from Q prime. So let's look at the Q primes. So if we're looking at this location here, Q41 is not going to generate a moment because it's acting in the same axis. Q34 would have generated a moment, but it's 0, so nothing there. Q12 prime is 0, so it doesn't matter. Q23 is the only one that is acting there, so we'll write the effect of that one, which is Q prime 23 times H times H. Okay, you have to multiply it times the length about which it's acting, and then times the moment arm. Okay, so it's Q23 times H times H. And then we also have to add the contribution of Q naught. We're ultimately trying to solve for Q naught. And Q naught, the torque generated by it, it doesn't matter what axis you're looking at. The axis could be here, it could be here. The equation for it is the same, always. And the equation is 2A Q naught. Okay, so area enclosed by Q naught times that. This is 0, so we can actually solve for Q naught. Q naught equals -1/2 Q23 prime, which ends up equaling VZ over 6H. So that's big right here. All right, we're basically done, almost. And so now we know that we're looking for the real Q's, but we have the Q primes and the Q naught, so we just add them together. So Q12 equals Q12 prime plus Q naught, Q23, same thing, plus Q naught, Q34 prime plus Q naught, and Q41 plus Q naught. So we just plug in the values. We have all the values over there. It's VZ over 6H, negative VZ over 6H, VZ over 6H, and 5 VZ over 6H. So at this point, a lot of these problems will be done. They just want you to find the shear flow and find the maximum stress. So we would just divide by a thickness at a certain location. We'd be done. This problem, it wants us to find the shear center. So how do we find the shear center? The way we do that is, let me see. I don't remember how to do that. Okay. So the way you find the shear center, you would be given, right, here we're given this structure. And we're told, yeah, VZ is acting here. Right, we have these things here. So now, in the equation that we used here, we used this distance 0. But now what we're going to do is vary that distance by some variable, and we're going to try to find that variable so that the moments produced here don't produce any twist. I'll just write it out. Hopefully it makes sense. So we're going to assume that VZ is not acting there, but it's acting at some location from that point. That's a distance E. Okay? So VZ times E has to equal Q23 prime H squared, same thing we had before, 2H squared Q naught. Okay? The reason we do this is because with this equation now, we're going to have new values for Q naught. Basically, we solve again for Q naught. So if we solve for Q naught, it's going to be VZ over 6H squared H plus 3E. Okay? And now solve for that Q naught, we now have different values for Q12, Q23, Q34, and Q41. So it's VZ over 6H squared H plus 3E. 6H squared. Almost done, guys. Hang on. So, I mean, it's the same thing for that first portion there. All right, so we have these new equations for the Q's. All right. And now, the way we solve for that variable E, right? So they're asking about the shear center. All we're interested in is finding that E. We'll get a value for it, positive, then we know the distance from that original point where we can find it. If it's negative, then it's in this direction. And the equation that we use is the rate of twist equation. If you guys remember how to find theta, right? So theta from the torsion chapter is 1 over 2 GA line integral Q over T ds. Remember, these line integrals are actually really easy. So if we write it out using these shear flows that we have here, it's 1 over 2 GA Q12 H over T plus Q23 H over T plus Q34 H over T plus Q41 H over T, right? So go one side by one side. And the key here is that if this shear force, VZ, was acting at the location of the shear center, this rate of twist would be 0. So we set this equal to 0, and we plug in those equations for Q1, 2, Q23, so on and so forth. We have, basically we could simplify this to Q12 plus Q23 plus Q34 plus Q41, and that equals 0. Plug in that, VZ is a known value, H is a known value, everything's a known value. We end up getting E equals -1/2 H. Okay, so if VZ was applied at the location E equals -1/2 H, then this wouldn't have any rotational deformation. It's important to remember that this is in the shear center. The shear center is the variable Y SC, right? So remember the centroid was here, right? Now we know E is -1/2 H, so -1/2 H from the original location. Okay, so we go -1/2 H. So this right here is YSC, which in this case YSC would equal -H over 6. And so that's the shear center. If VZ was acting at the location H over -H over 6, then this thing wouldn't twist. That tells us that it's acting in this location from the problem statement. It is resulting in some twisting deformation. We can quantify that as well. We're not going to go through that. That's in the next chapter, I think. And so that's it for today. What's up? It helps a little bit? Yeah? Let me move my stuff in. Go ahead. Oof, that's exhausting. Jeez. What's going on, man? No problem, man.
I will say you are head and shoulders above the other TAs that had this one.
Yeah?
Thank you very much.
I appreciate that. Just leave a good review at the end. That'd be dope.
That's the plan.
Yeah. All right.
I had a quick question about the homework.
Okay.
Problem 5.5, I think.
Uh-huh.
So,
What's your name? I'll keep an eye out for
turn up the.
it. We've definitely done
I was just trying to do the moment thing that you were doing, like if VZ times 0 is equal to all of that,
Uh-huh.
QAQ, with like this geometry.
Okay.
I got, for Q naught, I got this answer using this, but then I tried solving it like a different way, and I got half
See ya.
of this.
Yeah.
So I'm trying to figure out like why it's different.
What's the different method that you use?
So this is basically the way that you just did and the way he did in class.
Uh-huh.
This way is like the torque, the total torque of each, like Q1, 2 coming here, and then Q2, 3 coming here. This is the O point. But they give different values. So I'm not sure. I was wondering if I could look at the or
Solution? Yeah. Let me stop.